Good morning. For those of you who don't know me, my name is Kevin Myers. I'm a network architect and co-founder of IP ArchiTechs. We're currently the largest MikroTik consulting firm in the world. We have engineers in 6 time zones on 3 different continents, and I wanted to take some time to talk to you about using the MikroTik CHR as an MPLS router. If any of you were in Berlin last year, we did some testing with MikroTik CHR for a BGP border router. And we tested different hypervisors against each other to see what that would look like and what the performance would look like. And the results were actually kind of surprising because we found out that HyperV was the best hypervisor for MikroTik CHR, and that kind of surprised everybody. I got a number of comments after that everybody said, I can't believe HyperV is the best hypervisor, but you know, so it is. So for this year, we decided to do something along the same lines, but tackle MPLS, because a lot of people ask us about, can I use CHR for MPLS? You know, what can I do with the CHR as an MPLS PE router? So we decided to do some testing on that, and these are the results. So I'll give you a little bit of background on myself before I get started. I've spent about 20 years now in networking and network engineering. We designed and built networks on 6 different continents. We've built things all over the world. Antarctica is the only one we haven't hit, so if anybody knows anyone in Antarctica, let me know. And I'm a MikroTik certified trainer and also hold various MikroTik, Cisco, and Microsoft certs. I'm very, very passionate about being involved in the network engineering community, so there's a number of groups that I belong to you should check out if you have time. Packet Pushers is very, very popular in network engineering. If you don't listen or subscribe to their podcast, you should check them out. I've been on a couple of their shows and also done some blogs for them. If you're a WISP and you like talking about WISP topics, there is a Facebook group called WISP Talk. We talk about MikroTik and things related to WISP topics, so if you're not a part of that group, you should go on Facebook and check it out. It's very, very helpful. I'm also a delegate for Network Field Day. Networking Field Day is a group that goes to Silicon Valley in the US and talks to a bunch of different network vendors about what's coming next in network engineering. What are they developing next? So we've done that a number of times, and there's a bunch of helpful information in network engineering if you're interested in that. You can find me on the MikroTik forum as IPA Net Engineer. I'm always on there answering questions when I have time. And also on Network Collective. Network Collective is a podcast and Slack channel that you can get access to that is network engineers around the world. So those are all great resources if you want to learn more about network engineering, either for service provider or for data center enterprise. And then I wanted to tell you just a little bit about IP ArchiTechs. We were founded about 7 years ago as a consulting firm in the US. And since then, we've expanded a little bit to do work kind of around the world. And one of the things that we did that we thought was important was to expand in multiple languages. So we now support, I think, 4 or 5 different languages for our engineering team. We have 2 offices in the United States. We have 2 offices down in South America, in Maracaibo, Venezuela, and in Buenos Aires, in Argentina. And so we have engineers on our team that speak English, Spanish, Italian, and Portuguese. So, and Serbian. I can't forget Serbian. We have Serbian on the team as well. So, so that's something that we've been working on to make sure that we have engineers that can support you in MikroTik 24 hours a day, 7 days a week, in multiple time zones, so that you can always reach an engineer that's up when the sun is up. And we do consulting. We do managed networks. We do network monitoring, load testing, and development for our clients. Those are a few of the things that we do. One thing we don't do actually is sell hardware. We are purely a consulting firm. We only sell our services and our time and the time of our engineers. And most recently, which was new for this year, but it wasn't the case last year, is we are now in Europe. We opened an office in Niš, Serbia in 2018, so that we now have engineering resources in the +1, +2, +3 time zone to cover Europe as well as Africa and parts of Western Asia. Okay, so let's talk a little bit about the CHR as an MPLS router. What is the goal of this presentation? And I always make this joke when I give this presentation that I have this slide in there for Yanis Migas if he's sitting out there, because if you ever take the MikroTik trainer course, he will make you put this slide in. So for those of you that haven't taken it, there's a pro tip for you, not to get yelled at by Yanis. But the goal of this presentation is really to kind of tell you what our expectations were when we tested the router. What are the performance characteristics of the CHR as an MPLS router? You know, when you put something into a hypervisor, you always lose a little bit of power when you're not running on bare metal or in a container or something like that. So understanding that and what the performance characteristics are is very important. what are the best practices when you deploy the CHR as a router, especially as an MPLS router, because MPLS changes things very much. You're getting in between layer 2 and layer 3 headers, and you're adding MPLS labels, so that changes packet forwarding a good bit, changes quality of service, changes queuing, changes a number of things in your network. So understanding how that fits in, especially in context of a hypervisor and a vSwitch, is very important. And then also looking at the benefits of using the CHR versus a router board or a CCR. There's a lot of times when it makes sense to use a router board or a CCR as an MPLS router. And more commonly, today there are times when it makes sense to use the CHR as an MPLS router. And we'll go through a few of those use cases as to when it makes sense to use the CHR versus a CCR or a router board. So let's talk about hypervisors. This is something we covered last year, and have gotten into more depth, and we've studied more about how the different hypervisors affect the MikroTik CHR and the characteristics of it. Probably the single most popular hypervisor that you're going to find is VMware. VMware kind of started this whole thing. They've been doing virtualization for a long time. They do have a free version that you can use, and a lot of people are very, very familiar with ESXi in its various forms. The other one, which actually has their headquarters right here in Vienna, is Proxmox. Proxmox is a front-end GUI for KVM, if you're familiar with KVM as a hypervisor. It makes it look and act very much like VMware, so that you have a GUI for being able to deploy your VMs, manage HA hypervisor hosts, things of that nature. And then last, but certainly not least, is Microsoft Hyper-V. And Microsoft Hyper-V, we're finding, is getting an increasing role with MikroTik and using it with the CHR. And I don't have any concrete data on this, but I did talk to the MikroTik developers last year in Berlin as to why we saw Hyper-V perform better in the BGP tests. And I think the general consensus, and this was a bit of guessing, we didn't validate this, but that there were drivers already available for VMware and Proxmox when you're dealing with the para-virtualized interfaces in the hypervisors. But when it came to Hyper-V, there really wasn't anything readily available, so the MikroTik development team had to do a bit of work to get the drivers built to support Hyper-V. So I think that work actually ended up paying off because Hyper-V seems to do better in general on the CHR. So unlike last year, a really interesting note about Hyper-V, it is actually the only hypervisor that currently supports MikroTik CHR with MPLS. Now that's not to say that you cannot go run ESXi or KVM and put CHR with MPLS on top of it, but there is a post in the MikroTik forum, if you go read, that there is currently an issue with the way MTU is handled in ESXi and KVM, because the way they break down packets and send them into the vSwitch and out the physical interface is very, very different than the way Hyper-V handles it. And there is a bug that I think will eventually get fixed, or maybe a bug is not the right word, it may just be a mismatch in the way that the MTU is handled. But what you'll notice is if you put the CHR into ESXi or KVM, you'll notice very, very different throughput speeds. And a lot of it is because there's fragmentation happening at the hypervisor layer and at the vSwitch layer when you're using ESXi and KVM. That doesn't happen in Hyper-V because it deals with the MTU in a very, very different way. So if you need very low speeds and you don't need very much throughput, then you could use ESXi or KVM, but our general recommendation in the testing that we've done, and what I've seen other people that have run the CHR as an MPLS router, is to use Hyper-V. And the main thing that is different about them is in ESXi and KVM and in Proxmox, the way the packets are broken down to be sent out the physical interface is using buffers that are arranged into 64K sizes. And that's the way they both handle that. And something about that seems to create an issue with the CHR, especially if you need to run like a jumbo MTU for your MPLS network and your MPLS PE. There's a challenge there, and it creates a throughput issue, a serious performance issue in throughput when you're using this in in ESXi and KVM Proxmox because of the way the buffers are arranged to transfer the packets out. Hyper-V, on the other hand, does not do it that way. Hyper-V has a completely different buffer assignment for the way it moves packets through the hypervisor, and so it actually does not suffer that issue, and you can put jumbo frames and jumbo MTU into Hyper-V without issue. So again, and this is covering what we already talked about, but the reason I don't recommend VMware and Proxmox is because of the buffer handling and the issues that that there are on the MTU. And I didn't put it on the presentation, but if you're interested, I'll send you the link for the MikroTik CHR thread on the forums that explains in more detail the issues between all three hypervisors. So one of the things that we're going to look at as we dig down in the details here is looking at which platform is better. And that doesn't always mean which is better overall. Usually, as with all things in networking, there are trade-offs, and it really boils down to your use case of what you want to use MPLS for, and what services you want to deliver off of MPLS. Because one of the things I always say about MPLS, people ask me as a network designer, why should I run MPLS? And I say, well, MPLS by itself really doesn't do anything. It's the services that you enable on top of MPLS that are the real secret sauce. Those are the things that really help you to take very, very complicated things in an ISP network and make them uncomplicated. Or in a data center. Data centers are very commonly using MPLS now for client isolation. We had one data center we built with MikroTik that was for crypto mining. They were hosting crypto miners to be able to mine cryptocurrency, and they needed to isolate their clients. And one of the ways that you could do that is with VRFs in MPLS. And so that was a very, very helpful thing to go through. We're going to look at throughput capabilities. What are the throughput capabilities of the different devices as far as the CHR versus the Telera-based CCR or the new 4011, which is an ARM-based processor. And then we're going to look again at the MTU throughput concerns on the different hypervisors. So let's take a look at kind of the design of these different platforms and what they were designed for. And one of the things that you're going to notice right away is that x86 was designed for heavy computational work, a higher power draw. It's going to chew up the most amount of power, but it's also going to deliver the best performance when you have to move a lot of packets. Things that are heavily computational, OSPF and BGP are included in this. You'll find that you can get larger OSPF networks or BGP networks when you're dealing with x86 versus Telera because there is a limit that it hits. And looking at throughput, if you look at it at 1530 bytes, which is our MPLS MTU, which allows for a 1500 byte handoff, and then again at 8970, which is actually 9000 MPLS MTU bytes for a larger frame size. You need more CPU and power in the x86 to move the data at the same speed as the CCR. And that, again, comes from the hypervisor layer. You're putting one operating system on top of another, so you're always going to lose a little bit when you do that. But some of the benefits that you gain, I think, are pretty good. And so, you're only going to lose maybe 10 to 20% when you do this, as you look at it compared to the Telera. So you're really not losing a whole lot, and you're gaining a lot in functionality. And then you look at the x86 MTU handling, and this actually can be a very, very big key point in deciding which platform you're going to use, because if you have a customer, or if you're an ISP, and you have a customer that wants a certain MTU size, you're going to notice that we have some very different MTU sizes down here as maximum. And typically in all virtualization, they normally top out about 9000 MTU, and that's mainly because server NICs and server IPs and the operating systems normally do not go above 9000 MTU. That's typically where they're at. Conversely, if you look at the Telera, you can support up to 10,222. So if you have a client that wants you to hand them off 9216, which is a very common packet size in Cisco and Juniper networks, you can hand that off with MPLS if you need to, because you have enough MTU overhead. And then looking at the throughput and the CPU on the Telera really was optimized for packet transfer. It was optimized to be the highest amount of packet transfer at the lowest power draw, and that was really the architecture of the board, which is why you see it sometimes struggle with things like BGP full tables or large OSPF areas, because the whole design of the architecture was not meant to be heavily computational like x86. It was designed to be low power draw, and so it does move packets very, very well. At the cost of the computational. And then on the throughput, it actually handles the throughput at different frame sizes a little bit better than x86. So when you're looking at the internet layer, normally if you look at the average of an internet packet size, you're going to look at somewhere between 500 and 800 bytes if you average out your packets. And so you'll find that the hardware routers tend to handle that a little bit better, but it's not so significantly better that it would steer you away from x86. And then what I didn't have last year in this column was the ARM processor, because we didn't have an ARM device that supported 10 gig like we do with the 4011, which is great. We actually run it as the border router in our data center in Denver, Colorado in the US, and it's been just a fantastic device. So it's kind of in between x86 and Tolera for performance. ARM is definitely lower power draw than x86, but it wasn't explicitly designed to be super low power like Tolera was. It was kind of a stated goal of the Tolera processor to be ultra low power draw. And then the frame size handling is very similar to Tolera. If you test it, you'll find that it's a little better than x86, but it's very, very similar to Tolera in that respect. And then the MTU is a little bit lower, but it's not really a major issue because the frame size is above most of what you're going to need and what most customers are going to ask you for. And it tops out on, I looked at my 4011, and it tops out at 9982 is your maximum. So that's what you're looking at for your comparison of the stats of the boxes. So let's take a look for a minute at the logical lab setup and what we built. We did this all on hardware, except for the virtual machine, which we put on a Baltic Vengeance. And in looking at this, we had a very simple network. We decided to do 2 PE routers. One of them is CCR 1072, and the other one is our CHR that is running on a Baltic Networks Vengeance box, which I highly recommend the Baltic Networks Vengeance box. We know Baltic Networks and have been working with them on their Vengeance box for quite a while in testing. And while you can use any server that you want to, the nice thing about that is it's very consistent. You have a consistency in the hardware platform and consistency in the interface cards. So as you're testing and deploying more of them, you can achieve more consistency in the way you deploy your virtualized environment. It also doesn't require a full rack. You don't need a 4-post rack. It's a very, very short box. I think it's maybe 12 to 16 inches in depth. So if you have a 2-post rack, or what we call a relay rack, you can put it in there and it makes things very easy because the ports are on the front. So that's what we used for testing here if you look on the left-hand side where our Vengeance CHR is. And we built that as an MPLS TE with a /29 connecting it into the P router. We also put a loopback on that because it's required for LDP and MPLS. We have 2 CCR 1036 8G2S Plus boxes that formed our MPLS core. And if you notice something that I'm going to get into in the next slide, these are all VLANs. We did this in what we call a switch-centric architecture, meaning the routers are not physically connected all in a line with cables. They all connect into the switch, and we use VLANs to connect them all together. And I'll explain why we do that in just a bit. So coming on into the core, we have another VLAN that connects the 2 core routers that is also /29, and then another VLAN here that connects the PE router. So we have a very simple small MPLS backbone and 2 PE routers that sit on either side of it. And then on top of that, we're doing what's called a layer 2 VPN in the MPLS world, which is a VPLS tunnel. It's commonly today, it's called an overlay if you keep up with things in software-defined networking. But it basically creates a layer 2 segment that you can either put VLANs in or leave untagged that will join any 2 points. If you're a service provider, a lot of customers will ask you for things like this. You may decide to use this for something like IPv4. We have ISPs that don't want to break up their subnets to send out to their towers and their WISP. So what they will do is they will put a /24 or higher back at their data center or back where their head-end bandwidth is, and then they will hand out IPs to their customers over the VPLS tunnel so that they can save IPv4 space. And that's a very, very common application of it today. And there's a number of other things that you can do with it. We've been seeing for people that are not ready to deploy IPv6 in their entire infrastructure, they will use VPLS to deploy IPv6 directly to customers. So you can extend IPv6 over a native IPv4 network if you're not quite ready to go dual stack in your network. So there's a lot of different benefits of having this technology in there, and then a number of benefits in having it exist as a virtual machine. So let's look at the physical test network. We talked about the logical, but physically it looks very, very different. If you look at it physically, everything connects into the switch. And I didn't put all the exact physical connections, but each device has 2 10-gig links into the switch. And the point of that is, one of the things we found in working with MikroTik routers over the years is that when you connect them into the switch and use an LACP channel to connect them into the switch, it seems to be a little bit more efficient. And some of the reasons that we've theorized that is true is because you're using multiple lanes into the CPU, you're balancing the traffic out multiple paths into the CPU across the bus because MikroTik is a CPU-based router. And unlike an ASIC-based router, which is moving packets at wire speed, you are having to move them in and out of the CPU, which means you do have limitations of interface buffers and bus. And so we find that the more interfaces that you add to a router and aggregate them using LACP bonding into a switch, it tends to perform a little bit better. It also makes things easier when you need to make changes because you're not having to move cables. Once your cables land in the switch, you just add VLANs to add new services. You don't physically have to visit it. We have a lot of customers that physical access is very difficult for them to go move and add cables. And so when you do the majority of your physical access up front, it helps make you operationally more efficient. And most recently, one of the benefits we're finding is DDoS mitigation and protection. One of the challenges you're going to have if you use either a QoE engine, like something like Proseam, or if you use a DDoS mitigation engine where you're going to do a NetFlow export. The more routers and more devices you add make it more and more difficult to do that if everything is connected traditionally, where the routers are all physically connected to each other with links in and out. Because you have to have a port out of every router to get all the NetFlow data so that your devices can detect an attack for your NetFlow export. Or in the case of quality of experience, if any of you have used a QoE engine like Proseam, that also is a challenge because the more devices you have, the more connections and boxes you need. Whereas when the switch is in the middle of the architecture, you can connect two 10 gig interfaces into a NetFlow feed or into a QoE engine, and you can send that traffic up that way using VLANs. So you can scale a lot more rapidly and a lot easier when everything is centralized in the switch. So that's a little bit of background as to why it's designed this way instead of connected all together. So we've got our MPLS TE as our 1072. We have another MPLS TE as our Vengeance router. That's going to be running our CHR. On Hyper-V. We decided to use Windows Server 2016, which is a little bit different than the Hyper-V headless version. If you're really, really into command line for hypervisors, and some people are, there's a Hyper-V headless version that's free, and you can either administer it via command line, or you can use there's a Microsoft Management snap-in console that you can use to administer it. I found it a little bit cumbersome, so I took the easy way out and put Windows Server 2016 in, and then put it into a Hyper-V role. And that made things a little bit easier. So that's what we have here on our Vengeance. We have our core switch, which is a CRS 317. We have our two MPLS core routers, and then we've got our other MPLS PE down here. So let's talk about the VM provisioning recommendations for Hyper-V and the things that you should do when you're doing this. And these are a starting point guidelines. I'm not going to sit here and tell you this is the only way to configure it. You should certainly experiment with your own settings to see what works best for your application. But at least for the equipment that we had and the tests that we were doing, we found that these settings worked fairly well. One of the things that was interesting that I found in the MPLS router as well as the BGP router is that when you're doing heavy packet transfer, assigning more cores to the device actually made the performance worse. And a lot of that has to do with the way the hypervisor schedules the traffic in and out, so that the more vCPUs you have, the more work the hypervisor has to do to try to balance it across all of those cores. Whereas if you use a lower number of cores, but make those cores dedicated 100% to the virtual machine, it actually yields better performance because the hypervisor doesn't have to think quite as much about what am I going to do with this traffic. It knows that it's dedicated for that virtual machine, and it can allocate those resources. I normally recommend a decent amount of RAM in the PE. You could get away with a smaller amount. The main reason I do this is if you're going to put a lot of customers into this, you may use this PE for full tables. I've seen MPLS PEs used as full table handoffs for peering with customers if you want to do that. In this case, we're doing it as a layer 2 handoff. You could do it as a layer 3 VPN handoff. There's a number of different use cases. The main reason you want to give it a lot of RAM is that you don't want to have to take it back out of service to reprovision it if you can help it. So if you have a lot of RAM available and you dedicate the hypervisor, which I strongly recommend, to just doing what we call network function virtualization. So don't put your monitoring server on the hypervisor. Don't go put your syslog server on the hypervisor. Dedicate that equipment to this task and only this task. And that's probably the most common mistake we see made in virtualization with people that want to use the CHR as a router, is they will put it on the same hypervisor that does all their applications, and what you really want is dedicated hardware. You definitely want to disable hyperthreading in the BIOS. That's one thing. Hyperthreading is another one of those things like the CPUs that it's great in shared environments if you have certain applications that are going to be sharing, like in cloud applications, where you're going to be sharing a lot of VMs across a limited set of physical resources. But when you're going to be doing high packet transfer and you're going to be dedicating the hardware to this task, you really want to disable hyperthreading because it actually will improve your performance rather than, having hyperthreading on is going to make your performance worse than if you turn it off, it improves the performance. You want to use CPU reservation. This is different in the different hypervisors as to what they call this. You'll find, I think, in KVM and ESXi, they call it, I think it's CPU affinity, where you can tie certain CPUs into a a specific VM. In the Hyper-V world, they call it a CPU reservation. So you're basically saying that I'm going to commit 100% of the resources that are available in this hardware platform for the hypervisor host to this CPU and to this VM for this task. The other thing you want to do is disable any of the unneeded VM components. If you build a VM, typically from an OVA into, or from an image in Hyper-V, it's going to come with some things you don't need, like a SCSI adapter. You may have a CD-ROM interface. You may have a floppy interface. Disable all those things because obviously you're not going to need any of those, and that improves the performance and stability of the virtual machine. And then even if you're not going to run a jumbo MTU, I always recommend in your hypervisor host that you increase the MTU on that to the maximum so that if you do want to run a larger MTU one day, you don't have to go back to the hypervisor and increase the MTU on the virtual switch and on the NICs and in all the different places. And then whether or not you choose to run a large MTU at layer 3 in your router, you still have the choice without taking the hypervisor completely offline. So we'll talk about the concept of testing, of the way that we tested this. We built a VPLS tunnel between the two PE routers so that we could test traffic into the tunnel and over the tunnel to see what it would be like. We tested the performance using implicit null in MPLS as well as explicit null. For those of you that don't know what that means or not familiar with MPLS, I'm going to go into that and what that means here in a couple slides and what the difference between those two is. And then we also looked at the performance at 1530 MPLS MTU bytes, which is a very common handoff type. If you want to hand off layer 2 with a VLAN and hand off 1500 bytes to the customer, 1530 is the MPLS MTU that you have to have, and correspondingly the layer 2 MTU. Now it gets a little bit different in the hypervisor world. 9,000 MPLS MTU bytes is the highest that we can go, whereas normally I'll normally use like 9216 or something like that in a hardware router because it's available, but because you only have 9,000 available in the hypervisor, that's the highest that you can go. Some performance considerations that you should think about when you're doing this. As I said before, dedicate the hypervisor to the CHR or maybe a few CHRs, but don't mix applications or other things in that you're virtualizing unless it's something you just need to test for a very short time and then turn back down. And that keeps your environments very sane. TSO, LSO offload, this is one thing that's very commonly not talked about, not known about. We brought it up in Berlin last year. In the interface of your NICs for your servers, there is this idea that TCP traffic can be offloaded in hardware to the NIC. They call it transmit segment offload, label segment offload. And it sounds like a great idea. Normally, it actually, when you're running a router on top of this, it normally does not do very well. Normally, you just don't see the best performance, and it will actually decrease your performance. So if you look at MikroTik's official recommendation in the forums and the testing that we've done, I think confirms this, that you should definitely disable those. And clock speed. Typically, you're going to be better off with a higher clock speed and fewer cores than you are with more cores at a lower clock speed. Again, putting everything on a small number of cores that have a lot of power increases the performance of the virtual machine. So probably one of the most important questions is why would you do this? Why would you go through building a hypervisor and going through all this work to install Hyper-V and go put the CHR on top of it when you can just go buy a CCR or a router board and do this in hardware? Probably one of the biggest use cases I see for this is to avoid the potential for looping in layer 2 when you're trying to make your MPLS PEs highly available. And what I mean by that is normally, if you want to hand off to a customer, maybe a couple different handoffs because that customer wants to be highly available, you could put that into an LACP channel and you would have 2 links going to the customer. But one of the challenges that you would still have is that by having 2 of these routers that are both in that same VLAN, you have a point of loop that can be created. Now, you can mitigate that with spanning tree, and you could have spanning tree block it, and we have done that in the past. But it's not my favorite way to go because using spanning tree from a design standpoint for me is kind of a last resort for something like this. I would much rather find a different way to deploy it than depend on spanning tree because you can get a lot of unpredictable behavior with spanning tree sometimes. It can often cause you more heartache than it solves when it's deployed for a use case like this. So if you have 2 physical routers, that's really the only choice that you have is to use something like spanning tree. But if you use a CHR, you can have 2 hypervisor hosts connected together that form your failover because you have 2 different servers that form your Hyper-V cluster. And then you can have a single virtual machine that rides on top of those two. And because it's only active on one at any given time, you're not at risk for a loop because it's only a single instance of that PE. So for those of you that need to maintain a high SLA to your customers and hand off highly available services, this is a great use case for using the CHR, is using highly available hypervisors. And then you can have 2 different tunnels going into 2 different points without worrying about the potential for a loop. The other thing it's very helpful for is you may have a need to isolate your PE routers for different services. You may need to take PE routers and dedicate them to full table. You may want to take them and dedicate them just to a specific customer. And whatever that use case is, whatever it is that you need to do with it, having multiple hypervisors that you can spin up multiple CHRs gives you a lot of flexibility. And again, it's an idea we call operational efficiency. The less you're having to go out to your physical sites and touch things and plug things in, the better off you're going to be as far as how you can operate. And you can also automate these things. We use Unimis a lot. I know Thomas Kiernak is here, is one of the creators of Unimis. We leverage Unimis a lot to do a lot of automation and orchestration with MikroTik. And there's a lot of things that you can do with it. And if you can automate these different tasks and spin things up virtually or logically with VLANs and VMs, it's going to make your life a lot easier than continually putting hardware routers out at these core locations. Okay, so I promised that we'd talk about implicit null and explicit null, kind of what those are, why they're important, and how they fit into MPLS, and the reason that I'm bringing it up. So this is actually one of the first ways that people discovered that there was an issue with ESXi and KVM. Basically what they are is when you have an MPLS network, instead of having routes that define the destination of your traffic, if you think of a routing table and you have a route to 10/8 and it will point to a next hop, and your traffic will look for that route and it will go to that next hop based on what's in the routing table. In MPLS, the routing table is only a guide, but it exists, but it's actually not what forwards the traffic. The MPLS forwarding table is what forwards the traffic. So a label is assigned to a route. You may get a label assigned to that 10/8 route, pointing to a next hop. But when you actually get into the fib and the forwarding of traffic from interface to interface, it's that label in MPLS that actually brings that traffic from one interface to another. And the reason this is important is if you look at the typical default operation, I'm going to back up a couple slides here so that you can see this, of MPLS, you have what's called a penultimate hop pop. And if you can see the pointer here, these 2 routers in the middle are always going to label MPLS traffic. But MPLS by default does something called penultimate hop popping. And what that means is if it knows that the end destination is going to be going into a non-MPLS network, like we have a computer here that's not running MPLS, it's just an IP on an interface. If MPLS knows that it's going to take the label off that interface, it will actually take the label off 1 hop before it gets to the very last hop, which is why they call it penultimate hop popping, because they're removing that label 1 hop before. Now, some very common reasons for doing this are quality of service. For any of you that run quality of service in your network, if you've ever run MPLS, the way you set quality of service in MPLS is using the experimental bits, which is a field in the MPLS header. But what you can't do is if there is a DSCP tag, let's say you're a voice provider, and you want to mark EF on your voice traffic in DSCP, the MPLS routers on the way are not going to see your voice marking when that packet is in flight going across the core, because the MPLS experimental bit is on the outside of that traffic. So if you're stripping that MPLS label right here at this router on the far side, that will actually begin to use that DSCP marking for EF again and provide quality of service on that traffic at this edge router, the PE. So that's a very common reason why people want to use implicit null. On the flip side of the coin, if we go over back to this and go to explicit null, it does the exact opposite. It will keep the label on the traffic to the very last point on the network. So the label is actually removed at that last router before it goes to the non-MPLS segment. And one of the reasons you might use this is if you want to rely on MPLS to do your quality of service and use that MPLS experimental bit for quality of service, you might want explicit null on instead of implicit null. Now, one of the things that's really interesting about this is what they found when some guys were testing it. It was almost 2 years ago, I think. Is that when implicit null was on in ESXi and KVM, the performance was fine. The performance was generally what they expected. When they turned explicit null on, which does require a little bit more CPU overhead, as we'll see in the testing, the explicit null actually caused the performance to go down by 80 or 90% in ESXi. It was very, very bad, and in KVM. So there were a lot of issues there, and that's kind of how they discovered that. What we found in Hyper-V is they pretty much perform fairly similar at higher frame sizes. At lower frame sizes, there's definitely a difference in performance between the two, and you're going to see a little bit higher CPU utilization with the two. So one of the other things we wanted to do, normally I use Hyper for testing like this, but because right before we did this, MikroTik introduced the new multi-core bandwidth test on, I think it was 6.44 that it came in that you could do it. So we decided to take that out for a spin and see what that could do, and it was great. We had some great performance results now that we could use all the available cores of the CCR 1072 as well as the CHR that we have running on the other side. So let's take a look at the first performance test we did here. So we have our Baltic Vengeance box running on Hyper-V, server 2016. We're using implicit null, which is set in, if you go to the MPLS menu in Winbox and then you go to the LDP options, you'll see a little checkbox that says use explicit null. And you have to set that all the way through the MPLS network to turn it on or off. So this is with that turned off. And we had an MPLS MTU of 1530. And we saw about 4.4 gig in traffic. Now, just to give you a note on the way I do these are certainly not scientific results, but normally I will run these like 3 or 4 times to make sure that the test I'm getting is not an anomaly. So while I'm not going to tell you they're 0.1% margin of error, we do repeat them several times to make sure that the testing is consistent. So this was not bad. This is about the performance that we saw on the when we did the BGP test. We saw about 5 gig of traffic through the Vengeance box. And one note on the Vengeance device, it's the one we have has been around for a few years. It's an older Intel CPU. The newer Vengeance boxes have much more powerful CPUs, so I think they're getting closer to like 40 gig of traffic or 50 gig of traffic capability in the newest Vengeance boxes. But the one we have in our lab is a little bit older Intel Core i7 CPU. So now we're going to go to explicit null, which actually had a huge jump in traffic at the lower frame sizes. And I tried this over and over just to make sure that it wasn't a fluke. And it did see a huge increase in traffic when I applied explicit null, which is interesting because explicit null actually requires a little more CPU to move it through. But at the lower frame sizes, it seemed to do very well in moving more traffic through when you set that if you need to use 1500 for some reason. So now we're going to move up into the higher frame sizes and do an MPLS MTU of 9,000. And then I've got one more slide after this, and then I'll open it up for some questions about the presentation. The higher MTUs actually saw the CPU reduction drop. One of the things, if you're not familiar with how routers that are based on CPUs work, is that it's all about packets per second. It's really not about bandwidth. It's how many packets per second can I move in this interface to this interface. So if my packets are higher and they're a 9,000 MTU versus a 1,500 MTU, I'm going to see significant increases in throughput, which I only had a 10 gig interface available to this. So it might have been able to do more, but we limited it at 10 gig on the interface. And it only had 7% CPU usage. So this was very good. I could take this device and use it as an MPLS PE router and serve a lot of customers off this with being able to put 10 gig of traffic through it over VPLS. And then if you go to the other side, there's not really a big difference like there was in the 1,500 byte test. You have here 9.9 gig like we did on the other, but we did set explicit null. Now the one thing that did change, you'll notice, is the CPU utilization went up slightly. So it went up on average. The peak we saw was about 16%. On the slide before was 7%. So we're definitely moving more traffic through the CPU, even though we're not really moving any difference in the amount of packets per second that are going through the router. So that pretty much concludes the testing that we did and the things that we worked on. And I think we'll be doing some more tests with MPLS on the CHR and may get into some more topics at future mums. But right now, I want to open it up for any questions that you may have on using the CHR as an MPLS router. Any questions? All right. Well, thank you very much. I appreciate it.